If you've come across a video called James Webb Telescope Just Shattered Physics, I want to tell you up front what's actually in most of those videos. Vague talk about structures that suggest intentional design, light pulses from empty voids, and a Nobel Prize winner supposedly whispering about parallel universes. None of that traces back to an actual paper, an actual telescope reading, or an actual named scientist saying those specific things. It's assembled from dramatic phrasing with nothing underneath it. But underneath all of that noise, there is a real scientific story here, and it's been quietly one of the most genuinely disruptive results to come out of astronomy in the last few years. It doesn't involve the matrix, the multiverse, or anything watching us from beyond space-time. It involves something almost more interesting than that. Actual galaxies showing up in Webb's images that appeared to be too big, too bright, and too mature to exist as early in the universe's history as they clearly do. And a very real, very public scientific argument over what that means that's still playing out in papers being published this year. I want to be fair to why this specific rumor took hold so easily, because it isn't coming from nowhere. Unlike some of the other space myths we've covered on this channel, this one is rooted in a genuinely surprising, genuinely significant scientific tension that respected astronomers have openly called puzzling, surprising, and even used the word impossible to describe in their own peer-reviewed papers. That's rare. Most fields of science don't use language that dramatic in a formal publication. So when a clickbait channel finds a real quote using a word like impossible, it's incredibly tempting to just run with it, strip away all the careful qualifiers and follow-up context, and build an entire video around that one word. So that's what this video is actually about, where every single claim traces back to a named researcher, a named institution, and a paper you can look up yourself. Let's start with what Webb actually saw. James Webb. Space Telescope's entire reason for existing is to look further back in cosmic time than any instrument before it. Because light takes time to travel, looking at extremely distant objects means looking at light that left them an extremely long time ago. So peering deep enough into space lets astronomers effectively look back toward the early universe itself, not long after the Big Bang. Webb was specifically engineered with its infrared instruments to catch the faint, stretched-out light from galaxies that existed within the first few hundred million years of cosmic history. The reason Webb needed infrared instruments specifically, rather than the visible light cameras most people picture when they think of a telescope, comes down to something called redshift. As the universe expands, the space that light travels through stretches along with it, which stretches the wavelength of that light toward the red end of the spectrum. And for light that's been traveling for over 13 billion years, that stretching pushes it well past visible red, into the infrared range entirely. Hubble, Webb's predecessor, could see some of this, but Webb's instruments were built from the ground up specifically to catch fainter, more deeply redshifted infrared light than any previous space telescope, which is exactly why it could reach back further into cosmic history than anything that came before it. According to a 2023 paper by Bunker and colleagues, published using Webb's NIR spec instrument, one particular galaxy called GN-Z11 was confirmed spectroscopically to be a remarkable object with extreme properties, observed as it existed just 430 million years after the Big Bang, meaning we're looking at light that's been traveling toward us for roughly 3 billion years. That alone isn't the shocking part. Astronomers expected to find some galaxies that early. What shocked them was what those galaxies looked like. According to Boyette and colleagues, also writing in 2023, Webb's observations confirmed the existence of galaxies as early as 300 million years after the Big Bang, and at a considerably higher number density, meaning simply more of them, packed into that early slice of cosmic history than galaxy formation models had predicted. Separately, Deckel and colleagues described what they called a surprising excess of luminous galaxies at these extreme distances, and in one particularly striking case, described by Lucer and colleagues, Webb identified a galaxy that had already stopped actively forming new stars, meaning it had already lived through an entire active phase and quieted down when the universe itself was only about 700 million years old. Here's why that's such a big deal to cosmologists specifically, rather than just being a neat fact. Under the standard model of cosmology that's guided the field for decades, called lambda CDM, where lambda refers to dark energy and CDM stands for cold dark matter. Galaxies are expected to build up mass gradually. Small clumps of matter merge together slowly, over hundreds of millions to billions of years, gradually assembling into the large, bright, structured galaxies we're familiar with today. Under that model, galaxies as large and as bright as some of what Webb found simply shouldn't have had enough time to form that early. There hadn't been enough cosmic history yet for all that gradual merging and mass buildup to happen. It helps to think about this the way you might think about a construction timeline. If a building inspector expects a skyscraper to take at least a couple of years to build from the ground up, based on decades of watching other skyscrapers get built at a fairly consistent pace, and then someone shows them a fully finished skyscraper, standing exactly where an empty lot was only 2 months earlier, the inspector doesn't just shrug it off. They start asking hard questions. Was the timeline estimate wrong? Was something measured incorrectly? Or is there some genuinely new, faster construction method nobody had accounted for? That's essentially the position cosmologists found themselves in, except the construction timeline in question is the entire theoretical framework used to model how every galaxy in the observable universe came to exist. That mismatch is sometimes called informally within the field the impossible early galaxy problem. And it's worth being clear that astronomers themselves use language nearly this dramatic because the tension really is significant. It's not a fringe claim. It shows up across dozens of peer-reviewed papers. But here's where the story starts to diverge sharply from the shattered physics framing, because there's a second related puzzle that made things even stranger, and it involves black holes rather than the galaxies themselves. According to reporting from Pfister.org summarizing research published through 2026, Webb detected supermassive black holes sitting at the centers of galaxies that existed within the universe's first 1 to 2 billion years. And when astronomers compared the mass of those black holes to the mass of their surrounding host galaxies, the numbers didn't match anything we see in the nearby modern universe. In today's galaxies, a central supermassive black hole is typically somewhere between about 1 and 0. 5% as massive as the total stellar mass of its host galaxy, a remarkably consistent ratio, observed across countless nearby galaxies over decades of study. In some of these early, extremely distant galaxies, that ratio was measured at 10 to 30%. Read those two numbers side by side again because the gap is genuinely enormous, not double, not triple, but often somewhere between 20 and 100 times higher than the ratio we see locally. These black holes appeared to be almost absurdly overmassive relative to the galaxies supposedly hosting them, which raised an obvious and uncomfortable question. How do you grow a black hole that big, that fast, in a universe that young? It's worth explaining briefly how astronomers even measure a black hole's mass from this far away, since you can't exactly put one on a scale. According to the standard method described in coverage of this research, scientists look at gas swirling around the black hole at extreme speeds, close enough to be caught in its gravity. That gas produces specific spectral lines, essentially chemical fingerprints in the light reaching Webb's instruments, and the faster that gas is swirling, the stronger the gravity pulling on it must be, which in turn implies a heavier black hole sitting at the center. This method has worked reliably for decades when applied to nearby well-studied galaxies. The overmassive black hole puzzle emerged specifically when astronomers applied that same trusted method to the earliest, most distant black holes Webb could detect, and the resulting mass estimates came out looking wildly disproportionate to their host galaxies. There's also a completely separate, though related puzzle sitting alongside all of this, which is where the phrase Hubble Tension comes from, and it's worth explaining clearly because a lot of the clickbait videos blur it together with the early galaxy problem as though they're the same thing. They aren't. The Hubble tension refers to a persistent disagreement between two different ways of measuring how fast the universe is currently expanding. One method, based on observing relatively nearby stars and supernovae, tends to produce a value around 73 kilometers per second per megaparsec. The other method, based on the cosmic microwave background, essentially the oldest light in the universe, left over from just after the Big Bang, tends to produce a value closer to 67. Those two numbers have refused to converge for years across multiple independent research teams using different instruments, and it remains one of the genuinely unresolved puzzles in modern cosmology. It's real, it's significant, and as of now it still hasn't been fully explained. This particular disagreement has actually been simmering in the field for longer than Webb has even existed. Astronomers using the earlier Hubble Space Telescope had already noticed the two measurement methods weren't quite agreeing with each other years before Webb ever launched. What Webb added to the conversation wasn't a resolution to that tension, but rather more precise, independent confirmation that the discrepancy is real and not simply a result of one particular telescope's instrumental quirks. Having a second, more advanced instrument arrive at a similar disagreement made it considerably harder for the field to write off the tension as measurement error alone, which is part of why it's remained such a persistently discussed topic. But it's also, again, a different puzzle from the early galaxy and overmassive black hole story, even though a title like Shattered Physics tends to smash both of them together into one vague, catastrophic-sounding claim. Precision matters here because conflating two separate open questions makes each of them sound more apocalyptic than either actually is on its own. So let's go back to the early galaxy and black hole puzzle specifically, because this is the part of the story with the most genuinely recent and genuinely fascinating developments, several of them published just in the last few months before this video. Scientists responded to the impossible early galaxy problem. The way scientists respond to any genuine anomaly, by proposing multiple competing explanations and then testing each one against more data. According to a survey of the research published on ARXO summarizing the field's thinking, the leading candidate explanations included the idea that early star formation might happen in short, intense bursts rather than steadily over time, artificially inflating how bright a galaxy looks at any given snapshot. The idea that the earliest stars might have formed with a different, more top-heavy mix of masses than stars form with today, producing extra brightness for the same amount of total mass. The idea that measurement techniques themselves might be introducing selection bias, systematically picking out the most extreme, brightest examples while missing more ordinary ones, and simple modifications to how certain early universe physics is modeled within the standard cosmological framework. Let's unpack a couple of those a little further, because each one is a genuinely reasonable, testable scientific idea in its own right, not just a vague handwave. The bursty star formation idea suggests that instead of forming stars at a steady, predictable rate, some early galaxies might go through short, intense episodes of rapid starbirth, followed by quieter periods. And if Webb happens to catch a galaxy in the middle of one of those bright bursts, it could look far more massive and mature in that single snapshot than its actual averaged-out stellar population really is. The top-heavy stellar mass idea suggests that the earliest generations of stars, forming from primordial gas with a very different chemical makeup than exists today, might have skewed toward producing more large, extremely bright stars relative to smaller ones, meaning the same total amount of matter could produce noticeably more light than an equivalent modern galaxy would, simply because of what kinds of stars that matter turned into. Notice what that list does not include: intentional cosmic design, evidence of an older universe hiding behind our own, or a break in the laws of physics themselves. Every explanation being seriously tested is a refinement to how we model galaxy formation and measure brightness and mass, the normal, unglamorous work of science catching up to a genuinely surprising observation. And in 2026, some of that work paid off directly in ways that meaningfully calmed down at least part of this tension. In May 2026, NASA published research led by Katherine Chorowski, a graduate student at the University of Texas at Austin, working with data from Webb. According to NASA's own release, titled plainly, "Webb finds early galaxies weren't too big for their britches." After all, Chorowski's team found that some of these apparently oversized early galaxies are, in fact, considerably less massive than they first appeared, because black holes actively feeding on surrounding material inside those galaxies were making the whole galaxy look artificially brighter and bigger than its actual stellar mass justified. Strip out that black hole-driven extra light, and a meaningful chunk of the original impossible galaxies stopped looking quite so impossible. To picture what's actually happening here, imagine trying to weigh a house by measuring how bright it appears at night from a distance, and assuming all of that light is coming evenly from the whole structure. If it turns out a huge portion of that brightness is actually coming from one single, extremely intense floodlight mounted on the roof, in this case, the black hole actively devouring surrounding gas and radiating enormous amounts of light in the process, then your estimate of the house's overall size, based purely on total brightness, comes out far too large. Chorowski's research essentially identified that exact kind of floodlight effect happening inside a meaningful number of these early galaxies. And once it's accounted for, the underlying galaxy turns out to be a much more modest, far less record-breaking size than the raw brightness measurement originally suggested. That same basic idea, that black holes were distorting our measurements rather than genuinely rewriting the rules of galaxy formation, kept showing up across multiple independent 2026 papers, looking specifically at the overmassive black hole side of the puzzle. In June 2026, research led by Madison Brooks, analyzing stacked spectra from roughly 2,000 early universe galaxies, found that these previously reported overmassive black holes were likely observational outliers, produced by researchers naturally gravitating towards studying the most luminous, most detectable active black holes, a form of selection bias that made the overall population look far more extreme than it actually was, once a broader, more representative sample was analyzed. Then, in July 2026, a separate paper by Alessandro Trinca and colleagues, published in Astronomy and Astrophysics, proposed a specific physical mechanism for why these black holes appeared overmassive in the first place. The idea, in plain terms, is that some of these early black holes may be growing at extraordinarily fast rates, a phenomenon called super Eddington growth, in a way that actually hides some of their X-ray emission, one of the key signals astronomers normally use to accurately gauge a black hole's true mass. If that emission is being suppressed by the physical conditions around a rapidly feeding black hole rather than genuinely absent, then estimates based on standard methods could be seriously miscalibrated for exactly this population of extreme early objects. The term super Eddington refers to the Eddington limit, a theoretical ceiling on how fast a black hole can normally absorb surrounding matter before the radiation pressure produced by all that infalling material pushes back hard enough to slow the process down. Under most conditions, a black hole feeding right at or below that limit behaves in fairly predictable, well-studied ways. Trinka's research explores what happens when a black hole is feeding faster than that theoretical limit would normally allow, a more extreme, less commonly studied regime, and finds that under those conditions, the surrounding material can actually become thick and dense enough to absorb and redirect a meaningful portion of the black hole's X-ray output before it ever reaches our telescopes. That's a genuinely elegant potential explanation, because it doesn't require inventing new physics at all. It simply says that our standard mass estimating technique might be systematically underperforming in this one unusual extreme feeding scenario. And earlier still, in research published through the Astrophysical Journal Letters and covered by physnerd.org in May 2026, a team led by Mohammed Latif proposed a specific formation pathway for how these particularly massive black holes could form directly at cosmic dawn without necessarily requiring the extremely long, gradual buildup process that seemed physically impossible, given how little time had passed. Their paper, titled directly How Overmassive Black Holes Formed at Cosmic Dawn, works through the physics of exactly how you get a black hole that large, that early, using known physical processes rather than anything exotic. Put all four of those 2026 results together, and you get a real unfolding scientific story that's genuinely more satisfying than any invented shattered physics headline could be. Astronomers spotted a real startling anomaly using a brand new, extraordinarily powerful telescope. Multiple independent research teams proposed and tested several competing explanations over the following few years, and by 2026, a meaningful portion of that anomaly is being resolved through a combination of better measurement techniques, corrections for selection bias, and new physical models for exactly how black holes can grow so fast so early, not through any revision to the fundamental laws of physics themselves. That does not mean the entire early galaxy puzzle has been fully solved. It hasn't. Several of the papers referenced here are explicit that some genuine tension remains even after accounting for these black hole and selection bias effects. There are still galaxies that look more massive, more mature, or more numerous at extreme redshifts than the standard model comfortably predicts, and researchers are actively continuing to refine both their models and their measurement techniques to close that remaining gap. The honest state of the field, as of mid-2026, is that this was a real, significant challenge to standard galaxy formation theory. A meaningful chunk of it now looks like it was driven by measurement effects rather than new physics, and a smaller, genuinely open piece of the puzzle is still being actively worked through. That's a very different picture than physics has been shattered. It's the picture of a field working exactly the way science is supposed to work. A surprising observation, a period of competing hypotheses, incremental correction as better data comes in, and an honest ongoing acknowledgement of what's still unresolved. None of that requires abandoning general relativity, inventing older parent universes, or treating a Nobel laureate's speculative comment as a secret warning about the nature of reality. It's worth pausing on that last point specifically because it's a favorite technique of these videos. Taking a real scientist's genuine, careful hedge speculation about an open theoretical possibility and repackaging it as an ominous, certain prophecy. Serious cosmologists really have discussed, in academic contexts, highly theoretical ideas, like whether some early universe puzzles might eventually point toward modifications of standard cosmological models. That kind of open theoretical exploration is completely normal in physics. Brainstorming boundary-pushing ideas and then rigorously testing them against data is the entire discipline working as intended. What's not normal and not honest is stripping away every qualifier, every if, every one possibility worth exploring, and presenting the remaining fragment as a flat, terrifying certainty. You can see this pattern clearly if you ever manage to track one of these videos back to its actual source quote. A researcher will say something like, "One speculative possibility, among several we're investigating, is that our current models may need refinement in this specific regime." A perfectly normal, appropriately hedged scientific statement. By the time that sentence has passed through 2 or 3 rounds of paraphrasing for a dramatic voiceover, it becomes, "A leading scientist warns the universe as we know it may not be real." Nothing was technically invented outright. The original quote genuinely exists somewhere upstream, but everything that made it careful, honest, and scientifically responsible has been sanded off in the retelling. If you want to check any of this yourself, here's exactly where to look. Search Bunker 2023 GNZ11 NAR spec for the spectroscopic confirmation of that extremely distant galaxy. Search Chorowski 2026 NASA Early Galaxies for the direct NASA press release on black holes making early galaxies look artificially oversized. Search Latif 2026 Overmassive Black Holes, Cosmic Dawn for the Formation Mechanism paper in the Astrophysical Journal Letters. And search Hubble Tension on its own, completely separately, if you want to read about the genuinely still unresolved expansion rate puzzle, which deserves its own careful treatment rather than being folded into this story. Every one of those searches leads to a real institution, a real named author, and a real publication, not a vague reference to unnamed scientists or an unquoted Nobel Prize winner. There's a broader habit worth building here, the same one we've talked about on this channel before with other space stories. Real astronomy comes with names attached. A graduate student at the University of Texas, a specific spectrograph aboard a specific telescope, a journal you can search by name, a publication date you can verify. When a video instead offers you vague, unnamed authority, scientists are stunned. A Nobel laureate is warning, researchers don't want to admit. And without ever actually naming who, where, or in which paper, that absence isn't a coincidence. It's usually the entire tell. That test works on practically any space video you'll ever come across, not just this one. Before you let a dramatic title convince you something has upended physics, look for exactly 3 things in the video itself: a named researcher, a named institution or journal, and a specific checkable claim rather than a vague description of impossible data. If a video has all 3, it's very likely reporting on something real, even if it's presented with more excitement than necessary. If it has none of the 3, you're almost certainly watching narration built entirely on vibes, regardless of how confident or urgent it sounds. So no, James Webb did not shatter physics. What it did was hand cosmologists one of the most genuinely productive scientific puzzles of the last decade. Real galaxies, real black holes, real measurements that didn't initially fit the standard model. And then, over the following few years, an entire international community of researchers went to work on it, publishing paper after paper, testing explanation after explanation, gradually narrowing down which parts of the puzzle were measurement artifacts and which parts might still require genuine refinement to our models. That process is still ongoing in 2026, and it will likely keep producing new results for years to come. If anything, that ongoing process is the actual reason to find this story exciting, rather than the invented apocalypse a title like this promises. A field of science that can spot something this genuinely strange, argue about it openly across dozens of competing papers, and then steadily work its way toward a clearer picture using nothing but better measurements and more careful modeling, is a field doing exactly what it's supposed to do. That's a far more interesting story than physics simply breaking, because physics broke is the end of a story with nothing left to explain, while what actually happened here is the middle of one, with new results still arriving practically every month. If you'd rather understand the real, ongoing scientific argument than watch a fake countdown clock attached to a vague apocalypse, subscribe, because this specific story, the early galaxy and black hole puzzle, is still actively being resolved paper by paper, and I'll keep bringing you the real updates as they land, with the actual researchers' names attached every time. And if there's a specific shattered physics or broke the universe video you've seen that you want fact-checked, tell me exactly which claim caught your attention in the comments, and I'll dig into the actual research behind it.